Okay, ground motions designs. So, in earthquake engineering practice, uh, the stru- if the structural engineers, when they design their structure for dynamic response, what they need is they need a suite of accelerations time history that represent earthquakes that will go in underneath their buildings. So they want pretty much they want an earthquake time history record, and that becomes the work scope of a geotechnical engineers. So part of our job is provide a suite of earthquake ground motions that uh, either like by history record or like a synthetic, but synthetic ground motions is very complicated, like is out of the scope of this class. But for our jobs as geotechnical engineers, we need to provide those ground motions uh, that form the peer database. We talked about this before. There's a peer ground motions database uh, that allow us to dig into it and then find the ground motions that it needs for earthquake engineering analysis. So the very first step is before even like the soils go, the ground motions of the earthquake go through the soil layers. We need to start from selections of ground motions that at the bedrock level. So that will be our engineering jobs. That not only one ground motions, but we will select like uh, a suite of ground motions. Rule of thumb is 7 ground motions that it needs to represent our earthquake scenario that we want to design. So to get started, the very first step in order to get obtain those ground motions, we need to design the walk accelerations time history. So that's what we do. And in order to get those acceleration time history, we need to establish the target accelerations response spectrums at the walk level. So this picture shows you like the end products, and this end products start with the response spectrum, which is the black line over there. The solid black line is the target response spectrums representing the soil sites that you want, or like the soil sites that you anticipate how the response spectrum look like. And all this color wiggling curve right here, those are earthquake records. So each lines over there will stand for one earthquake records that the engineers obtains from the peer website. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There may be 10 earthquake motions here. So uh, the earthquake motions are recorded as acceleration time history, but after you transfer that into response spectra, then this how this look like. So this is lateral period rather than like in the time domain, and this is spectral accelerations. So that's the very first step again, is to establish the response spectra, and that's 3 ways to obtain that. So first is from deterministic method. We talk about this in the next slide, which means using those NGA models, next generations attenuations models, or the ground motions predictive equations, and those models or equations are based on earthquake parameters like Matthews and distance. We'll talk about this in the next slides. And the other approach will be a little bit easier, is using the code-based design, the IBC code, which is the International Building Code. The latest version is 2018. It give us like guidelines and simplify the procedure to give kind of like a rough estimates on those design spectra. So this designs like a spectrum. The black lines here is from the IBC. So IBC compared with the code-based design, compared with the deterministic site-specific design, this is more simple. But you could imagine this is in a way that is more global. If you want more site-specific results or site-specific models, those NGAs and or GMPE will be a better choice. And if you want to be to be even more like an in-depth or like even to the next level of analysis, is use PSHA, probabilistic hazard analysis, to create a uniform hazard spectrums. So for this class, we will focus on the first two. So what is the GMPE, the ground motions predictions equations or attenuations relationships? Those are empirical equations uses to predict ground motions at specific sites as functions of these earthquake parameters. The two most important parameters are the magnitudes and distance, and also some minor site conditions, tectonic settings, and fault type. Those kind of like parameters also allows you to as an input to change or to alert your results. And the equations that for those predictive equations exist for PGA, spectral accelerations, peak ground velocity, areas intensity, durations, all this like intensities parameters we talk about. At the end of the day, what you did is try to correlate the earthquake intensity. So there will be many different like offers. There's many different like equations based on the researcher, their preference on what kind of intensity they want to relate it to those earthquake parameters. So end up those equations pretty much are statistical analysis using statistical regressions to relate the earthquake intensities to those earthquake parameters. So pretty much like you could imagine it will be for example, you'll be a PGA. The PGA functions of those earthquake parameters, maybe magnitudes and distance and so forth, so on. The early on models, the equations is not too bad, but the latest models, you could imagine you could have like 50 parameters. You could get like quite complicated, and a lot of statistical mean or regressions method right there. So all this model is keep updating, because again, like each earthquake, a major earthquake happens, that means like more data to come. So the whole thing got evolving. So the very first models of Abrahamson or Silver, I think, come out with 1997, and a decade later, there's they update their models to be Abrahamson and Silver 2008. So. And that's still not like final form of those models or predictive equations. Is still in a field that still keep evolving. And I try to give you some very simple examples. So this Joyner and Bond to 1988 here is kind of like the very first attenuations models in the early days. So this pretty much is quite outdated already. In today's standard, this is way too simple. But I want to introduce this to you just want to get you started, and in some homework problems, maybe exams, maybe I ask you to do some simple calculations based on these equations, because simple enough that you can handle by hand cal. But so the idea here is pretty much just try to correlate or try to relate some earthquake intensity parameters, this case the PGA, to earthquake parameters like magnitudes and distance. And the distance here, they have specific uh, definitions, so which is based on the RJB plus x square of square root. So that this is the distance mean right there. And we talk about what is RJB in lecture 1. So those models is kind of like, you give like update like with time. And I think this lecture, or this at least this lecture recording, I want to focus maybe on a little bit more IBC, but I will go back to introduce you as a program which is a spare heat that have a lot of GMPM earthquake models by Abrahamsons and Silver, and those are important peoples to introduce you how to use a spreadsheet program to calculate this response spectrums. I will upload the spreadsheet to CanFax too, but we'll come back to this. But before we get into the details, or like a little bit more complicated analysis to establish the response spectra, I want you to introduce the IBC, the code-based design. But before we get there, the code-based design, I want to reintroduce or try to reinforce the concept of shear wave velocity, which is very helpful to for us to define the stiffness of a solid site. And we will need like the shear wave velocity to help us to do the IBC code-based site classifications. So pretty much like V sub S here, I want you to remind you, is representing the soil stiffness, and we want when we will need these parameters to do site classifications. And also VS30. So VS30 means like the shear wave velocity at the top 30 meters of your soil profile, and this is the calculations of a VS30, because very likely real life soil profiles, you will not, soil is not homogeneous materials, so you will have different layers on different layers, and each layers you have your own shear wave velocity. And for site classifications purpose, we are interested in the top 30 meters, so we want to know the average shear wave velocity at the top 30 meters, and that's how we calculate it from using these equations. Pretty much just taking the mean of the reached mean of the shear wave velocity based on the thickness of each layers. So let's get into the IBC code. The most updated versions is 2018. I put 2006 right there because that is the versions that I have. I cannot go back to the campus, to the library, to get the most up-to-date manual, but I will try my best I can to see what have changed, and the new update 2018 versions, you can find out more information on this link. So the whole idea of the code-based design response spectrum is they kind of like get a little bit more global data to give pretty much like a ballpark estimations of the response spectra. So this is the response spectrums that the IBC code describe. So this is a target spectrums, and with some simple or standardized what they try to do is like form response spectrums that used to be like a curve, or like a little bit more site specific, and then into a more general kind of like a form, something like this. So they simplify a curve into like a couple points right there, and now if you define those, if you can like define those like terms right there, T0, TS, TL, SD1, SDS, then you're able to establish a simplified response spectrums. And different part of the curve, you have different equations. So from this within like from 0 to t naught, this part of a line here is represented by these equations, and this kind of like a curve here is represented by these equations, and this part is represented by these equations. So the idea is once you're able to find out those like terms, then you can define a simplified response spectrums. And those are the procedure. So I list out the 2016 procedure, and I believe like the 2018 code base like designed, it didn't change much, but you better double check. But I take a quick look, it didn't change much from the 2006, but there was some change on the parameters that I will talk about. But this is the basic procedure. Again, like at the end of the day, we want to obtain the ideas. If they want to obtain those parameters, and in order to obtain those parameters, you start from step number 1. So there's some USGS map, so United States Geological Survey map, and at the risk level of 2% in 50 years level. So this is a risk level. Then you can find the parameters of S sub S and S sub 1. And then the next, you need to classify your source site, whether it's A, B, C, D, E, or F. And this soil site classifications, you need the shear wave velocity that we talked about before. And then the code will provide you some tables to get the parameters of F of A is F sub V, and then you do the calculations to modify for S sub S on S sub 1 at the beginning. So those S sub S and S sub 1s, I mean the short period, second period spectral accelerations that is kind of related to the spectral accelerations of 1 second here. So this SD1. And FA and FV that you determine from tables are those are site coefficients, and then you modify with the damping. So you get the SM1, and then next you will get the SDS. So all this are code-based designed, and then and SD1, and at the end of the day, you will get the needed parameters. And this is the base here that like we don't worry about it for now, but like I focus on establishing the response spectrums. So end up like you will get you're able to find those parameters because like once you know SD1 and SDS, you can calculate T sub S, and if you know T sub S, you know T naught. So if you know T sub S and T naught, pretty much you can establish the shape of your response spectrums. We will do our quick examples together to walk you through how to do this. So those are the IBC building code. So this is 2006 versions. Highly recommend you to get to 2018 one. You need to buy it. But if you go practice in Geotech engineers, then like in your library, then you should able to obtain one manuals for the IBC code. So if you crack the code, you can get the S sub S. Pretty much it's like it's very global scale. So pretty much like once S sub S will be representing the eastern United States, and then you can find another S sub S representing the west coast of United States. And in exam settings, in homework settings, I will provide you the S sub S. So that's just pretty much step number 1, to find the S sub S and S sub 1 from those like map. And the next is to do the classifications. So this is the table of ASCE 705, and please check for the most updated versions. So this is the versions of 2005. ASCE is chapter 7. They may have updated that, but I just don't have the access to the library at this point. But anyways, like you realize like for each different type of soil. So this represents the site classifications. So if you have rock sites, your shear wave velocity will be within this range. And if you have like a soft clay site, you have a much lower shear wave velocity. And this could be VS30, the 30 meters, the shear wave velocity, the average shear wave velocity of the top 30 meters. So based on the shear wave velocity for a site, then you can find out the your site classification, see the A to E. F will be complicated, will be like very special soils, where likely the soils that are subject to are very subspecies to solid refractions to be happens. So after you know the this site classifications, and like at the beginning you also figure out the S sub S and S sub 1, then you will find out you can find F sub A and S sub V according to this table. And this is the table for 2006 versions of IBC, and I managed to find the IBC table for 2018, and you realize the number between the two, they are different. So make sure when you go practice, make sure you always find the latest versions of the building code. And if you practice maybe 5 years from now, there may be even like a more updated versions than this one of the 2018 versions. But at the end of the day, like the same thing here, you want to find out F sub A and S sub V. And also like based on the map, you can find out the T sub L, the long period time. So let's try a quick examples together. So the examples, you have 18-story buildings to be built in Auckland, and those are the informations for the buildings. And this is working on the Hayward Fault, and this is cables to do Matthews 7 earthquake events, and then like your site is 6 kilometers from the source, from the earthquake source, and the site is have 20 feet of sand right here on top of 12 feet of clay with the unit weights and also the shear wave velocity given to you, and the clay is also on top of this another layer of sand, so the unit weights and also the shear wave velocity here. So now at this site, we also give you the S sub S and S sub 1 parameters, and also the T sub L. So the needed like map parameters for you to do the IBC code are given to you. First, it asks you to find the shear wave velocity for the top 30 meters for this site, and also the next asks you to plot the IBC design spectrums. The next step, you will estimate the building total base shear at a short period of time, and at the end of the day, I will walk you through how to select the ground motions from the PA websites after you have established your design spectrums. So this is kind of like the solutions that I've created. First, like you find the shear wave velocity using the formulas. So this is for the top 30 meters. Actually, this is about 30 meters. And then like using the equations, we got the shear wave velocity. The velocity is about 974. And if we go back to our ASE soil classifications, the ASE 7, which is this table here, and the soils sites tell us it's not liquefiable, so it's not it's for sure it's not like classification F, and this is 975. So this is between 600 and 1200. So this is a site D. So we know that this is a stiff soil site based on the calculated shear wave velocity. So we know this is site D. And it's given that the S sub S, S1 and TL parameters, Now we know that we are site D, and then we know those parameters, so we can go back to this table. So we know that we are site D, and we know that our set S of S is 1.8. So we know our FA parameters is 1 here. The same thing, we know our S of 1 is greater than 0.6, and we are at site D, so we know that our S of V is 1.7. So with those two parameters, we find F of A and S of V, and then we follow the procedure. We can calculate the SMS and SM1, and then after knowing those two, we can calculate SDS and SD1. So knowing SDS and SD1, it get us close to establish the design spectrums, and we know our T sub S and our T naught right there. So it further help us to know, like, what we need on the x-axis for design spectrums. So all these equations that I put on there is pretty much just from the code. So if you crack the IBC code, you will find all the needed equations, which is here. So all those needed equations you will find in the IBC code. So pretty much we have what we need. Then we can plot our design response spectrums. So when you do this, you need to do it on Excel or graph paper. Now I just do really quick on my computer. So, oops. So this is your design spectrums, and the x-axis is the time period, and y-axis is the spectral response accelerations, and this is in terms of gravities. So the very first point is, well, first of all, we know the T naught. The T naught is calculated as 0.123. So this is 0.12. So this is the T naught, and T naught is corresponding to the SDS. So SDS is 1.2 G. So this is 1.2. and this is the T naught. This is our first point, and the this part of equations here, if we go back to the to our the IBC code, pretty much this equation, this part here is this equations. So when time equals 0, not the time, is the period. Be very careful. There's a difference between time and period. So this is, if the period is 0, then pretty much like at the y-intercept, the spectral accelerations is SDS times 0.4. So we know that our SDS is 1.2. So here is 1.2 times 0.4, which is 0.48. So we know this is like 0.48. So this part, let me use purple for the response spectrums. So this part is like this. And then we know this curve will response spectrums will go flat until we're hitting a T sub S, and T sub S for our case is 0.614. So here, so this point stop at 0.614. So this is the T sub S. And then now this curve will go down until we're hitting 1 second. So this will just go down like this, and this pretty much is 1 second now. So this point is 1 second for the period, and the corresponding SD1 is so at 1 second the spectral accelerations is 0.737. So this part here is 0.737. So this is the spectral accelerations at 1 second. And then after that, so this is 1 second, this will keep going until we hit the T sub L, which is given as 2 seconds. So this is 2 seconds equals to T sub L. And this part of equations here is S sub A equals to SD1. Sorry, this is S. So this is SD1 divided by the period. And after that, this part of equations is equals to this one. So it's SD1 times T sub L divided by the times the period, not the time, the period square. So that's how we establish the response spectrum based on the IBC code. And we will talk more about using the NGA model. Okay, so we have already established our design spectrums using IBC. The next step is to estimate the building's total base shear. And if we go back to our IBC code, the last two steps is finding the seismic base shear force. So if you look at this formula, this is very similar to what we have been learning in the previous slides. That we conclude the base shear is equals to the spectral accelerations times the weight of the buildings. And in fact, this C sub S here is a modified spectral accelerations. So this C sub S here is equals to the spectral accelerations at different period of time, and then divided by modifications. So pretty much this is this C sub S is the spectral accelerations. But there's 3 different cases when the period difference. So let's try to solve these examples together, finish examples. So the first case we want to look at is the short period. So now, okay, so here is the solutions on finding the base shear force, and it depends on the period, and the period is sorted into a short, long, and very long period. Pretty much is the color coded here to represent the spectrums. So the short period is less than the T sub S. Long period is between the green area here between T sub S and T sub L. And whatever greater than T sub L is the very long period. So at each different period representing the response of the soil, you are expecting a different base shear force, and given by a different formula for the C sub S. So for the short periods, the C sub S is equals to SDS. So SDS we solved it already in the previous procedure, and pretty much is the spectral accelerations at this a flat or this constant spectral response at the maximum here. So it's equals to SDS divided by 2 correction factors, the R and I. So the R is the response modifications factor. You can find this number from the ASCE 7 table 12.2-1, and the I is the important factors for the build for your structure. So you can correct this number from a structural manuals too. I think like ASCE 7. There's a table to describe the important factors, depends on your building type. So you plug in R and I, then you can find the C sub S. Likewise, the C sub S at other period, you will have different formulas, and you're using SD1, and this T here for the middle period is the lateral period of the building, which is given to you here. For our case, it's 1.7 for this particular examples. So after calculating the C sub S for the 3 different period of time, and we take the maximum one before we design for the worst case scenario, it is 1.2. So this becomes your spectral accelerations for your base shear calculations. And the base shear calculations, we know the shear force is equal to the weight of the building times the spectral accelerations. This case is 1.2. So that's the solutions for this example.